All right. Welcome back. Are there any questions? People have burning questions about last week. Right, last week we talked about ggplot a lot. Doing okay on the labs. I scored a bunch of the first ones. I didn't touch any of the second ones. Did you start grading any of the second labs,
Not
Angela?
yet. I plan to this week though. I'm a little behind, but I finished. But all of the lab ones, unless you submitted it super late, are should be done.
Okay. So we'll get to lab two soon.
Yep.
All right. So let's talk about probability. So tonight might be a review for a lot of folks, but we need to lay some groundwork and some definitions in order to do some more advanced stats is what we're gonna kind of build this up. So probably not new. We kind of symbolically represent probability of events as P of A, where P is the probability, A is some event, right? We might not write A, we can write H for probability of heads, right? Could be 0.5 and things like that. A key component here, as we're going to learn, is probabilities have to range between 0 and 1. So a probability of 0 means that event could never occur. Probability of 1 is that event always occurs. And so what we're generally interested in is something in the middle. And a lot of the statistical methods we're going to use are going to kind of rely on this. And like Angela's going to talk about distributions next week when we talk about these things quantitatively, right? We're talking about trying to define probabilities somewhere between 0 and 1. Now, there are sort of two major interpretations of probability. The bulk of this semester will be taking on the frequentist approach, but there's also the Bayesian approach. So let me first say, so the frequentist approach in general, like in 2 weeks, we're going to define, if you see in the title, something called the central limit theorem, which is sort of the crux of how frequentists make inferences. But broadly speaking, the notion or the principle that frequentists are taking on is that we have some sample, we have some data, right? And we know things, about the distribution, or like if we were able to take like a theoretically infinite number of samples, right? Then that's how we're going to make our inferences. Like we're going to learn in a few weeks. If we could do that, we kind of have some ideas of what that looks like, right? So Frequent just says, well, truth is out there, and I just have one little glimpse into what the truth is, right? Might be a very broad, general way to think about how a frequentist thinks about inference. Bayesians say my data is truth, right? And what I'm going to do in order to model like how close I am to the true answer is I'm going to generate lots of data to see how often I observe what I actually see, right? And so at the very end of the semester, we'll revisit and do a crash course in Bayesian methods in terms of like how that difference is. And if it's not entirely clear right now, that's totally fine. I'm more interested in having the frequentists like so, and we're going to see the frequencies are kind of predicated on this notion that if I could do this over and over, right? If I could run the same study and get a different sample, I'm going to get a different mean, for example, and I could do that over and over. And so to know where the real population or true mean is based upon knowing the, what it, if I were able to take an infinite number of samples of what that distribution looks like to get to that answer. Okay. So one of the first principles we need to talk about is the law of large numbers. So the law of large numbers simply states that as we collect more and more observations, our observed probability or observed proportions are going to converge to the true outcome proportion or probability. Okay. So let's talk about an example, or let's walk through an example. Classic flipping a coin, right? We expect to get roughly the same number. We expect the probability of getting a heads is 50%, right? Probability of getting tails is 50%. Now, if I flip a fair coin and I get, and it comes up, heads comes up on the first 10 tosses, what's the probability of getting a heads on the 11th toss? So it actually turns out to be, does anybody want to answer?
It's still 50%.
Thank you, Peter. Yes. you did not fall for the gambler's fallacy, right? Because each event is independent. But what the law of large numbers says, that the more and more coins I toss, I should have my observed proportion of heads to tails should converge to 50%. However, each coin toss is independent. So knowing what the first 10 coin tosses is does not inform what the next coin toss is going to be, right? So this belief that, oh, I got a lot of heads, I'm due a tails, that's called gambler's fallacy, right? And it's sort of a misunderstanding of the law of large numbers. Oops, I went the wrong direction. All right. And we can actually simulate that, right? So I have this little shiny app, and we can, control how many games we want to do, odds of winning, which I'm going to leave at 1 out of 2, which is like a coin toss, and I could do 20 runs. So after 100 coin tosses, so the way this works is if I get heads, I add 1. If I get tails, I subtract 1, right? So I can manage this cumulative sum. And so I have this blue line, right, which is 50, which is where I sort of would expect to land. And so here on this one, I ended up with -2, and then a +8, +12, +8, right? So we can do this over and over. I can do, 20, up to 20 at a time, and we could see, okay, I have some above, some below. And so at least in the first part of this semester, the next few weeks, what we're going to try to do is say, right, if I, after 100 coin tosses, I sort of expect to get 50 heads and 50 tails. But if I got 45 heads and 55 tails, do I suspect something wrong with the coin? What about 40-60? What about 30-70s, right? So what we're going to try to do is quantify how far away maybe from that expected value that we now suspect maybe there's something wrong with the coin. And then that variation is not because of random chance. Okay, so we could switch this. We could say, if you do 1 out of 6, you can imagine this is a game where you roll a die, and if you get a 1, you win. Anything else, you lose, right? And so after 100 games, we end up with -68, and we could do this over and over, and kind of see and simulate where these kind of expected values are going to be. Okay, so if we look at this, so here's one particular run after 1,000, right? And a lot of times we might look at this and say, wow, there's a lot of variabilities, and we're very far from 50-50 for a long way. But what we need to kind of consider is the scale on the y-axis, which actually also gets to sort of a data visualization principle. So what is the possible range of values we could have here, right? We could, right, if we got all heads, we could end up at +1,000 because we did 1,000 replications here. If we got all tails, we could end up at -1,000. So if I just take this plot, right, and scale it to what the actual range could be, we see this little squiggly line is this line, but we've rescaled it, right? So to me, I hope this helps a little bit. Like this, to me, this is my best way I can kind of visualize the law of large numbers, right? The more and more observations I get, the more my observed probability is going to be to the actual probability. In this case, it would be 0 because I'm doing a cumulative sum, but 50-50. All right. A couple other definitions. We could have disjoint or non-disjoint outcomes. So disjointed means they're mutually exclusive, right? So can't happen at the same time. You can't have a heads or a tails. Theoretically, maybe the coin can land, but I'm going to assume that's not possible. When we draw a card from a deck of cards, we can't have an ace and a queen, right? Now, non-disjointed are things like I can get a heart and a king, right? It could be the same card. You can get an A in stats, and you can get an A in 607, right? Those are not disjoint because both could happen at the same time. So we take these probabilities that we have for different events, and we can start to combine them together to define what we call probability distributions. So a probability distribution has a number of rules. First of all, you have to list all the possible events. All the events need to be disjoint. The probability for each event has to range between 0 and 1, and the sum of all the events has to equal 1 to be a fully specified probability distribution. So the simplest one we could define is a coin toss, right? So we can have heads, probability of heads is 0.5, probability of tails is 0.5. You can't get a heads and a tails. So they're disjoint. They each have probabilities between 0 and 1, and the sum of them is 1. So that's a fully specified. We could just take it a step more complicated. Well, what's the distribution for flipping 2 coins, right? So I could get a heads on the first and a tails on the second. Likelihood of that happening is 0.25. I could get 2 tails, or I could get a heads on the first, tails on the second, tails on the first, heads on the second, right? Each has a probability between 0 and 1. They're all disjoint, and if I sum them all together, it equals 1. So we have a fully specified probability distribution. We already kind of talked about independence. So that's kind of, so what we're really talking about, just to reiterate and to be clear, independence means knowing the outcome of a current event, or let me say, how do I say it? I'm sorry. Knowing the outcome events before the one you're looking at do not change the probability of the current event, right? So flipping a coin is independent. Knowing I got 10 heads does not tell me anything about what that 11th coin toss is going to be. Okay. Now playing cards is not independent, right? And if there was a movie and book from a few years ago, I think it was called 21, where students from MIT went to Vegas and played blackjack. And what they realized is that when you're playing blackjack, there is non-independence, because if I, let's just assume we have one deck of cards, a 52. And I see an ace of hearts played. Okay, so the probability of getting an ace of heart on the first thing is 1 out of 52. Well, let's say I'm looking for a king, a king of hearts. So the probability of getting a king of hearts on that first pick is 1 out of 52. Now I see an ace of spades played, or whatever, or ace of hearts. I can't remember what I said. What's the probability of getting a king of spades on that second card? It's now 1 out of 51, because we have one less card, one card's played. So they're not independent. So knowing the outcome of the first card tells me the probability of getting the second card. Now, in Vegas, it's kind of complicated because they use a lot of decks. But if you could keep track of what cards are being played and you're looking at your hand, and you could say, well, the likelihood of me getting that card that's going to allow me to win, that probability is going to fluctuate. And if you can keep track at the right moment, you can make a good bet, because the odds of getting the card you need is higher now than they were, right? That process is called counting cards. Now, it's not allowed in Vegas. If they catch you doing it, they kick you out. And they tried to fix it by they'll use 20 decks of cards so that you see cards playing, but that change in probability from each card being played is so small to not really be meaningful. Does that make sense? Okay, there's a question. How would you describe a probability distribution if there are too many outcomes to list? That's a good question. So you're talking about so we would be talking about a continuous probability distribution, and that will start next week. We'll address that question next week. So you're gonna have to hold on to that for a moment. All right, independence. Are we good on that? Because this is kind of now, if we're talking about say survey data or other kinds of things, sometimes we want to check for independence. So here we have a survey conducted in North Carolina, where individuals were asked whether or not they think guns protect citizens. And then we also collected some information about their ethnicity. So overall, 58% of respondents here said that guns help protect citizens. But the probability that the citizen thinks guns protect citizens and are white, given that they're white, is 67%. Black respondents said 28%. Hispanic respondents said 64%. So we can use this formula here, right? So if the probability of A given B equals the probability of A, then we could say those two things are independent. So in this particular example, the probability of A, in this case, is 58%. The probability of A given black, for example, is 28%. So they're not equal. So we would say there's a dependence between ethnicity and the response to this survey question, right? So a lot of times we want to check for independence in sort of survey type data. Actually, I guess we're going to introduce it a little bit here, Alexander, but we're going to go into detail next week when we talk about distribution. So a random variable is a numeric quantity whose depends on the outcome of a random variable, right? So we tend to represent it as a capital letter. And the actual outcome is represented by a lowercase variable. So, and then there's two kinds of variables we're going to be interested in. We have discrete random variables. So these are things that take on whole numbers, integers, right? Counts, that kind of stuff, credit hours. Then we can have continuous random variables, which are things like anything cost or financial, right? That's going to have decimal places, height, that kind of stuff. Anything that's kind of a real number, if you will. Okay. So let's give me 1 second to pull up this Shiny app. Switch from the other. Zoom is getting in the way here. Okay. So what I now want to introduce, right? So when we talk about heads or tails, we kind of intuitively have a sense of what we would call expected values, right? So the expected value for any coin toss is 50-50. Now, if I'm doing 100 coin tosses, the expected value for the number of heads is 50. Now, as I said, a lot of what we're going to do this semester is say, well, how far away from 50 do we need to get before we, suspect something's wrong with the coin? But expected value comes out a lot, right? So we talked about sort of basic descriptive statistics a few weeks ago, right? And so expected value is going to be our measure of a center. So when we talk about doing statistics, we typically want some measure of center and some measure of spread. The ones we talked about. So we have mean and standard deviation as sort of one set of measures of center and spread. We could use median and interquartile range, right? And we talked about that being a more robust statistic, but it's a different measure of center and a different measure of spread. So when we talk about probability events, right, we want a measure of center, right? And sometimes that measure of center is called the expected value. We're going to see there's kind of various phrases that we're going to use. So this is like another Shiny app to kind of show one way we could get this to simulation through a simulation. And this is actually something I built ages ago for a student who was in counseling psych who was interested in doing research with folks who have gambling addictions. So he's trying to find a way of like, how do I show, right, people who are falling for the gambler's fallacy, for example, how do we overcome that? And so if we go to this odds table, I actually pulled this from New York State. It's a bit dated, admittedly, but New York State publishes the odds for all scratch-off tickets on their website. And so this was for one of their particular dollar scratch-off tickets. And so the odds of winning $1 was 1 out of 15. The odds of winning $2 is 1 out of 11. I don't know why the likelihood of winning $2 was greater than $1. That's what it was. All the way up to, you could win $2,500, and that's 1 out of 618,000 scratch-off tickets have that. And so here, the only thing you can really adjust on the left-hand side is how many tickets, right? So the notion here for this student was, well, I'm going to show this to folks and have them play around with this and say, well, what happens if you buy 1 lottery ticket per day for a year? How much money do you think you're going to win or lose after a year? And so this is actually simulated data. And so you could see here on the second, it looks like I maybe on roughly the second day, I won $4 and then lost $1 for a bunch, won $2. Looks like I won $5, but the most I won all year was a $30 ticket. Okay. And so I could say, all right, better luck next year. So I can click new run. And so here's year 2. And after year 2, I ended up losing $148. I could go to year 3. I did a little bit better. I only lost $124, right? And so we can do this over and over. And I have this button here. So let's do it 10 years at a time. So I think 30, 40, 50, 60, 70, 80, 90. Let's say I live to be 100. I played 100 years. I've never come out ahead, right? And so this is, one, he was using it for sort of a psychological experiment or intervention. But but one of the questions, right, you might ask is like, if I play this lottery game, well, what is my expected outcome after a year, for example, right? So one thing we could do is take the ending point from the simulation and just simply calculate the mean, right? If we take the mean of an outcome after 356 runs, right, that we call that the mean, but we're going to also call that the expected value, right? Because we're talking about a probability event. Now we can actually calculate it, right? So that's doing it through simulation. So you see that kind of naturally how we can get there. So here's our formula for expected value or center. So if we go back and remember the formula for the mean, what do? We're taking the sum of all the values divided by how many we have. Well, we don't, so we're kind of doing that similarly here. So we're taking the probability of each outcome given what that is, right? And just summing across that for all the ones. And so that's our expected value of that outcome that we will also call the mean. So let's look at, we'll get back to the lottery thing in a second. Let's talk about another silly game that I invented, right? So here's a card game. We have a deck of 52 cards, and I'm going to let you draw one card. If you get a heart, I give you $1. If you get an ace, I give you $5, including the ace of hearts. If you get a $10, if you get a king of spades, I give you $10. Any other card, you get nothing. Okay. So first thing we want to do is actually write down and specify our probability distribution. So what are all the outcomes? So we could get a heart, but not an ace. Okay. So the probability of that is 12 out of 52. There's 13 hearts, but the ace doesn't count, right? So 12 out of 52. The probability of getting an ace, right, is there's 4 aces, and it's 4 out of 52. The probability of king of spades is 1 out of 52. And then there's 35 cards left. Okay, so anything else. So the sum of this column equals 1. So we have a fully specified model. But what we have here is like each outcome is not equally weighted. So that's what this x sub I component is, right? So in the case of a heart, you get $1, an ace is $5, a king of spades is 10, and anything else is 0. So when we're calculating that mean in terms of an expected value, we're going to take that outcome times the probability of that outcome, which is, we're going to take that 1 times 1252 is 12 over 52. 5 times 4 over 52 is 20 over 52, et cetera, et cetera. We sum this, right? And so we end up with 40 out of 52, or 0.81 approximately, which means if you play this game, you're expected to win 81 cents on the long run. Okay. But if I charge you $1 to play, that means your expected value would be losing 19 cents, right? So you have to take $1 minus the expected outcome, right? And so I know this is a silly game, but in essence, every game in Atlantic City and Vegas is designed to have expected values that are negative for you, meaning the house always wins in the long run, right? They're designed that way. So don't fall for it. I'm not going to criticize if you like to gamble, great. If you have fun with it, great, but just go in expecting to lose, right? Mathematically, you are going to lose in the long run. There are whole courses where you could just look at all those games. Now, this is sort of a picture of the full probability distribution. So we could see here each bar. So we have 0 to 10, right? So I didn't define 2, 3, 4, 6, 7, 8, or 9, right? So those are all 0 because those aren't possible outcomes. But the probability of getting 0 is a little over 60%. Probability of getting 1 is a little over 20%. 10% for 5, right? And 2%-ish for 10. So the sum of the height of all these bars equals 1, right? So we could see this as a probability distribution, but now we could see probability of all the possible outcomes given this distribution. So let's go back to our lottery ticket. So here I'm just defining a data frame with labels. This is the outcome, and here's all the values, and just some quick conversion. So here I'm just going to do a simulation. I have to do a product of the top by this. This just ensures I have all the combinations. And so I'm just going to do 1,000 replications. I go through. You could see here I lost $1. I actually ended up. Oh, this is a whole bunch of runs, 1,000 runs. So I won $9 all the way through. And so if I do this through a simulation, I can take the mean. So on this dollar lottery ticket, the simulated expected value or mean is minus 0.48, or essentially you're going to lose on average 49 cents for every lottery ticket you do. And here I can plot that probability distributions for using 1,000 replications. But we can actually calculate it exactly, right? So here's our table. So I can take 1 times 1 over 15, and right, so I get that cross product here. I'm going to sum that cross product, and I have to subtract 1 because it costs $1 to play. And so I end up, so the real expected value is you're going to lose 38.5 cents, right? So my simulation's off. I could probably make this 10,000 or 1,000 to get a little bit more accurate using the law of large numbers to my advantage, right? So my goal here is to show two things, right? In this case, we could, actually, this helps Alexander's question, right? What do you do when you have too many to list? You could do a simulation to try to get there. That's one way. We're also going to look at quantitative or continuous distributions, like I said, next week. That's another way, if that's the possibility. Or, but if you can list them all, you have this formula to calculate it. I just did another simulation there. Right. Okay. Okay. Need to take, because you're going to work on this, I think this week's lab. Is this week's the Kobe hot hands, or is that next week? I always get confused. I forgot to look at it. Anyways, is it this week, Angela? Do you know?
Yeah, this week.
Okay. If you haven't started the lab, fine. But if you started, one of the things I'm going to try to offset a question that often comes. You're going to be working in the lab, and if you're like me, you're going to kind of run the code in the RMD interactively, running it in the console, experimenting, type your answer. Then you're going to go click knit. And then you're going to realize my document has different numbers than what I just wrote about. Okay. So that's because we're doing some simulations here. You're going to play with simulations in the lab this week. Computers, right? So if you run it now and then I run it later, right, you would expect a different random number, right? So now there's a way we can get around this. So our programs, computers are actually not really good at randomization. They're heuristic machines. They're deterministic, and they tend to try to replicate. So what computer scientists have done, and I think have done a fairly good job, as we'll see, is they have written what are called pseudo-random number generators. And so they just have these heuristics that they run through a whole bunch of things based upon some input, and the output is more or less random. Okay, so let's talk a couple things. So, so here there's a built-in vector I think talked about before called letters, right? So if I call sample letters, each time I run this, right, I'm just essentially shuffling the letters. Now I could say I only want one letter. Oops, I can't remember the name of the parameter. Let's look at it. Oh, it's size, right? Okay. Right. So I could get 1 or I can get 2. But the point is, every time I run this, I'm going to get a different answer. And let me take this out, right? So you're going to see us use this. We're going to use sample a lot because we try to do simulations to explain some stuff. Or we could do it in terms of a coin. So a couple of other things, right? So I can define a vector. If I call sample, it just shuffles it. I can get 1. Now, if I want more than 2, right? In the case, some of the examples I've done tonight, flipping a coin toss a lot. If I add this replace equals true parameter, a couple things happen. Now each sample is independent, right? Because I'm allowing replacement. And a lot of times in high school, if we can meet in person, sometimes I've done exercises where we've had a bag of M&Ms or a bag of marbles and say, okay, what's the probability of getting a blue marble, right? Well, there's 10 marbles in here. 2 of them are blue. It's two. Now I pick a ball. What's the probability of getting, if I put it back, the probability for each one is the same. If I don't put it back, it's different. So this replace is a great way of doing sampling or simulations in R, and there's an equivalent in Python that ensures that there's independence. Okay. Now, the way the random number generators work in R and Python and really any program is there are these pseudo random algorithms. And the way it works is on some input. Now, by default in R, I'm pretty sure I'd have to confirm it, but I'm pretty sure it just uses the current time in milliseconds. Okay, as the seed, right? So there's a seed that goes into this algorithm. It does a whole bunch of stuff, and then on the output, it should look like a random number. So in this case, right? So if I set the seed and then call sample, a number between 1 and 100, if I set my seed to 2112, I get 6, and I can run it again. And I could do it over here. So if I say, so I could sample letters, but what I could do is say set seed, and I'll use 42 here. So I get QEA, right? And if I run it again, I get the same answer. Okay. So for those who are bothered with getting a different number when you knit, what you could do is just add a set.seed command at the top of your RMD file. And as long as everything runs in the same order, you'll get the same answer every time you knit. So this is kind of a handy thing, like if you're interested in reproducible research, right? And you have some kind of random process in your analysis, setting the seed could be a really useful thing. So you give your script to someone else and they'll get essentially the same answer. They should get exactly the same answer. But just to show that indeed, is it really random? What I've done here is I'm going to initialize a data frame with X between 1 and 1,000. And I'm looping over it. And I'm going to set the seed to that integer. So I'm going to say set seed 1, draw a random number between 1 and 100. Set the seed to 2, draw a random number, et cetera, all the way to 1,000. And so what I've done here on this plot here is I plotted the seed versus the outcome, right? Looks like noise, right? There's no pattern here. And in fact, we'll talk about correlations, but you have some intuitive sense of what correlations are, right? The correlation here is pretty close to 0, right? And that's good, right? So there's no relationship between the seed and the outcome, meaning the pseudo random number generator is doing its job and generating what looks to be a random number. Okay. So in the lab, moral of the story, you want reproducibility, put a set.seed function call at the top of your script. Every time you knit, you'll get the same answers. If you don't do that and you write your answer as like, I got 0.6, and then next time you run it, it's like 0.65, I get it. We understand, right? You're not going to be penalized for that. That's just the nature. But I wanted to provide some context as to, because we're going to do a lot of simulated stuff in this course. So it's kind of nice to know. And oftentimes I just set the seed in my R Markdown file behind the scenes in order to do that. And that sort of lays the foundation for probability. So next week we'll be kind of extending it to distributions, but I know this is a quicker lesson and we're happy to stick around and answer questions. Not all meetups will go short. Most of them will go long. I apologize, but we try our best. So I put the 1-minute paper link in the chat and yeah, ask away.
I have a question on the set seed.
Yep.
If you set it in the top or somewhere in your R Markdown, does it apply to like the whole thing? Because I found that I put it on one spot, but it didn't apply to like the other stuff.
Okay, so each time you're calling the random number generator, I think it's like the seed is being incremented. Okay, so let me see if I can do something here. So if I say set seed you know, 42, whatever. Pick whatever your favorite number is. I usually use 2112, but we'll use 42 tonight because I think that's also a fun number. So if I do, so I'm going to sample, we'll use the sample function from letters, and I'm going to say size equals 1. So I'm going through and I'm running my analysis, and I can go through and I'm going to get Q. And next time I'm going to get E, right? So now I come back and I do set seed. Oh, I got Q again. I get Q, then E. But like, then I come in and I put, you know, a different, I'm going to do, you know, just to differentiate, I'm going to pick 2. So now I come in and do 2. Now I get J. So if I come back, I'm still going to get Q on that first one, but now I get Y on that third one because I added something in between. So the order like you have to have the same number of commands running in the same order in order for it to really work.
Jason, you're muted.
Damn it, I muted to cough and then okay. So did you hear me say anything about the order matters in the free
That's
sequence?
where, yep, that's
Okay.
where.
All right, so one other thing is, like, if you're kind of changing things or you have different blocks or you're kind of in development, you could set the seed for each chunk is one way to approach it. And if you didn't know this, if you put a semicolon, you can actually put 2 commands on one line. Almost the only time I ever do this is like this, where I want to set the seed before I call this command, right? So this is a big where I'm generating some random number. So that would overcome your issue. So regardless, when I run this, or if it's an R markdown, that seed is always being set immediately before I do that particular random thing.
Jason, another question about the seed. So does the algorithm that R uses, does it ever change? For example, I mean, when R is updated to a new version and
So
you ran an
yes,
old program?
it's happened once. In the 20 years I've been doing R programming, I think when they went to, I want to say it was R 3.0 came out. We're on 4 now. They changed the default algorithm. And so I'm trying to remember. There is a way of setting which algorithm it uses, and I can't remember where it is. So in R's history, it happened once. And there were good reasons. There was some debate as to whether or not to change it. But honestly, I think it wasn't really a change in the algorithm. It was a change in the number of bits they used. So I think they went from like a 32 to a 64-bit algorithm, but it was the same class of algorithm. But this is a long time ago because I remember encountering it, and then for a while I used to specify the algorithm, but now I don't do that anymore. So let me see here.
So it's pretty reliable.
Yeah. Random number algorithm in R. Let me say set. So this is all generating. I don't want to let's say, let me see what random number algorithm is used in R. Merson Twitter. Okay, I guess. So if you want to go down this rabbit hole, I don't know a lot about how random number generators work, but it's sort of beyond the scope. I just done things like this to satisfy myself that it's working as I expect it to. I can look at it, Alexander. If you're interested, I could probably dig in.
Oh, no,
my
I was
archives
just
and find it.
curious. I'll leave that up to you.
Let's look at the random normal. Does it tell me? I feel like it was an option, like so. But the problem is it doesn't. Well, let's see here. No. What if I do RND? Is there? I think there's an RND. Or is it RND? Or is it RNG? No, I can't remember. Yeah, it's been about a decade since I had to change it or set it. So I can't remember off the top of my head. Other questions? You know where this gets to be a bigger issue is in encryption, right? So having good random number generators when you're encrypting things matter a lot. And so if you need to do encryption in R, it's in the digest function. So if you want to encrypt something, by default it does MD5, but you can see it has a whole bunch of encryption algorithms and some pretty good ones. So somewhere in here there might also be so you could set your seed algo. Oh, that's the algorithm. It's probably going to be defined by the encryption algorithm. But this is definitely a digression. Other questions?
I have another question.
Sure.
I'm just looking ahead of some of the assignments that are posted. So I know lab 5, there's an A and a B.
Yep.
And I'm looking at the schedule on when it's due. It only shows 1 week that lab 5 is due. So does that mean we have to do 2 of them in 1
Yeah,
week?
but they're each shorter. So, but they're two different parts of the topic. So hopefully it shouldn't take you really any longer than doing one lab.
Okay.
Anything else?
I have a question.
Professor.
Yep.
Go ahead, whoever's talking. I'll wait.
I had a question about the 1 minute papers.
Yep.
I believe those are due after every session, right?
Yes.
Is that correct?
Yeah. For those who are watching the recording right now, you should do it when you're done with the recording. If you're live, just try to do it right now. They're called 1 minute papers because they should literally take you 1 minute.
Mm-hmm.
They do count a bit to your grade, but we compile them all at the end of the semester. We look at them week to week, but we compile like in terms of, it's like you do it or you don't kind of thing.
Yeah, I honestly wasn't, keeping track of doing them, but I just realized this week that I wasn't doing them. So
Okay,
I'm gonna
so
start doing that.
Start now. Yep, you should be fine.
Yeah. All right.
If you miss a couple, it's not, you're not gonna. If you do the majority of them, you'll be fine. And we're only at the beginning, so you're in good shape.
All right. Thank you.
Yeah, you're welcome. Well, you can have, oh, why does this say 7 p.m.? Well, that's a mistake. Sorry about that. Everybody's here on there. I hope I didn't see a notice that anybody turned on earlier.
I believe someone else had a question after someone let me speak.
Yeah, oh, yeah, I don't know who it was. I couldn't see.
Yeah, that was me.
Oh, you have a question? Go for it.
Yeah, I was just wondering if you have any sample coding for this class in your GitHub account.
Sample code for what? I'm sorry.
For this station, like for probability and everything.
Well, this always comes up. I think it'd be interesting to do a whole class on simulations. it sort of depends on the question you're trying to answer. So for me, every simulation I do is a little bit different. So so far we've looked at the sample, but as we get into the distributions, we're going to talk about starting with the normal distribution, and for each distribution type, there are sort of 4 functions that you're going to use to work with them. So there's a D, Q, P, and R. And then the second part of the function is what the class is, right? So I kind of looked at, because I was looking for the random number thing earlier. So so there's R, and the one you're asking, so I'm only going to talk about this one right now. So the R class of functions is for random. So if I want to generate a random number from a normal distribution, I would use R norm. If I want to use, again, this is kind of peeking ahead, we'll learn about another distribution called the binomial distribution. So I could do R binom for the binomial distribution. So what I want for now, and we got a nice plot that will explain this when the time is appropriate. But you could see there's D, P, Q, and R with binom. Then I have D, P, Q, and R for norm. I could look at T, the T distribution. I have D, Q, P, right? So so they all have this. So if you need to generate random numbers, it's R and then the distribution you want to generate the random number from. So that is sort of the key piece to doing simulations, is like, so sometimes it's sample, sometimes it's, if you want to randomly draw stuff from a random distribution. So, I don't know if I'd want to necessarily go much further at this point, but if you're interested in simulations as we go through the class or towards the end of the class, happily do more, but we're going to use them quite a bit, because instead of deriving a lot of the concepts here through algebra or calculus or other things, we try really hard to do it through simulations or visualizations, right? So let's actually do this over and over. So sample's a great way to do it, right? So tonight we showed simulation for doing lottery tickets and simulation for doing coin tosses. We could write a simple simulation for picking cards, right? And in all those instances, I would just use the sample function, but I have to define the problem to know what I'm trying to, what kind of fake data am I generating? So there's no set recipe to do it. It's unique to each question that you have.
All right, thank you.
Yeah, no problem.
I have a question. Sorry.
Sure, Jonathan.
The simulations for the lottery tickets, are they the slides? Do you post them on your website, or?
Yeah, of course. Yeah. So in usually about an hour, a couple things you can do. So if you click, so here's last week's. So if I click on this, that gives me the HTML version. If you click this, you'll get the PDF version. And then if you want to really see, you can click on this GitHub link. I don't link to it directly. Usually talk about this a little bit further in the semester, but it's worth talking about. So this whole website is hosted on GitHub. This website is created using R and a package called Blogdown, right? So I'm using R everywhere. So here's all the source for the website. So what you might be interested is in the slides directory. So you can see here's the PDF, here's the HTML, here's the R Markdown file that I use to generate the slide deck. And so in some instances, like so tonight, well, I kind of showed the R code everywhere, but in some instances, I might not show the R code and only the output of the R code. And you're like, well, what was the R code that generated that? If you're curious, I show it if it's meaningful to the lecture. And sometimes I hide it just because it doesn't fit. And it's not something I want to talk about. I just want to talk about the output. But you can always go into the GitHub repo, and you could see Right. So here's a ggplot expression, right? And so you can see all the code used to generate the slide deck. So keep that in mind. So it's all there. And usually in the last class, I go in and show you, because this repo will just kind of fill in. I fill it in every week. At the end of the semester, you can always come in here and download a zip file, and you'll have the whole course materials copied to your local computer if you want.
All right, thank you. I appreciate it. Yeah, that's exactly what I was looking for, was the coding stuff. Thank you.
Yeah. Yeah, no problem. All right. Well, then let's call it a night. Excuse me. I will not see you guys next week, but you'll be in Angela's very capable hands. I'll see you guys in 2 weeks. And so have a good one. We'll see you soon.
Have a good one. Stay safe. Enjoy your vacation. Bye.
Thanks.